Good morning, everyone. Welcome to the course Stability Aspects of Structural Steel Design, Concepts and Applications. Let us continue our conversation on buckling. The last class, we talked about Euler columns. Leonhard Euler introduced the concept of buckling for long, slender columns in 1757. There are some assumptions of Euler columns. The column is considered to be an ideal column. It should be perfectly straight before loading. It should be made of homogeneous material and upon which load is applied through the centroid of the cross section. Material behaves in a linear elastic manner which obeys Hooke's law. The column buckles or bends in a single plane. The ends of the member are simply supported and the deformations of the member are small such that the term y dash square is negligible compared to unity in the expression of curvature y double dash divided by 1 plus y dash the whole square, the whole power 3 by 2. Hence, the curvature can be expressed as y double dash. The takeaway is that an ideal column is initially perfectly straight, made of homogeneous material, and the load is applied through the centroid of the cross section. The critical load is the maximum axial load that a column can support when it is on the verge of buckling. This loading case represents a case of neutral equilibrium. A pin-connected column will buckle about the principal axis of the cross section, having the least moment of inertia, which is the minor axis. The slenderness ratio is defined as L by R, where R is the smallest radius of gyration of the cross section, and buckling will occur about the axis where the ratio gives the greatest value. Now let us discuss about bothered boundary conditions for the ideal column. Let's now discuss about fixed Euler columns. What you see is a column with length L and the properties are EI. E is the modulus of elasticity and I is the moment of inertia. It is subjected to an axial load P and subjected to n moments m0. Along the direction, it is x, and in the direction perpendicular to the column, it is y. And we are talking about the buckled shape here, and we are going to look at the equilibrium configuration at point A. So we can see that a blown up version of that is given as here, the deflected shape as point A here, and the displacement corresponding to point A is V, the vertical displacement, at a distance x from the left-hand side corner of the column, and it is subjected to an axial load P. The end moment m0 is acting, and then the internal moment mi is acting at the cut section. We know m equal to minus ei into d square v by dx square is the moment curvature relationship for small deflection. The internal moment is given as mi is equal to minus ei into d square v by dx square. The external moment me is given as p into v minus m0. For equilibrium, taking moment about point A, we have counterclockwise direction mi minus me is equal to 0. We substitute the terms mi and me into the equation, we get minus ei d square v by dx square minus p into v plus m0 is equal to 0. This can be written as ei into d square v by dx square plus pv is equal to m0. Substituting p critical for p, we have ei into d square v by dx square plus p critical v is equal to m0. This is the governing equation, which can be further simplified by dividing with ei. We have d square v by dx square plus p critical by ei into v is equal to m0 divided by ei, or d square v by dx square plus alpha square v equal to m0 by ei, where alpha equal to root of p critical by ei. The solution for the ordinary differential equation is given as v equal to complementary solution plus particular solution. The complementary solution is given by this one, d square v by dx square plus alpha square v is equal to 0. So we put d square by dx square equal to the capital D square. So we have d square v plus alpha square v is equal to 0. We take v common, we have d square plus alpha square into v is equal to 0. b square plus alpha square is equal to 0 is the characteristic equation. So which gives the value d square equal to minus alpha square. Again, then this becomes d equal to plus or minus alpha I. We have to recall the roots of the form m plus or minus ni. The solution is e power mx into a sin nx plus b cos nx. Here m equal to 0, n equal to alpha. So the value of v is given as e power 0x because m equal to 0 into a sin alpha x plus b cos alpha x. So which gives the equation v equal to a sin alpha x plus b cos alpha x. This relates to complementary solution. Now we talk about particular solution. In particular solution, let a constant C be the particular solution for the ordinary differential equations, also known as ODE. A constant is chosen because the non-homogeneous part is a constant, that is m naught. So we have d square v by dx square plus p critical divided by ei into v equal to m naught by ei. So substituting C for v, we have d square c by dx square plus p critical by ei into c equal to m naught by ei. Since it's a constant, d square c by dx square becomes 0. So we have p critical by ei into c equal to m naught by ei. The ei on both sides can be cancelled. Therefore, c equal to m naught by p critical. So this can be substituted in the above equation. So v equal to a sin alpha x plus b cos alpha x plus m naught by p critical. The first two terms are complementary. The third term is a particular. Let us find the unknowns a and b from the boundary conditions. We know that dv by dx equal to a alpha cos alpha x minus b alpha sin alpha x. Because when we differentiate sin, we get cos. When we differentiate cos, we get sin. So that is why we get the value dv by dx equal to a alpha cos alpha x minus b alpha sin alpha x. Solving for a and b using the boundary conditions. We know that at x equal to 0, v dash equal to 0 because the slope is 0 at the fixed end. So when we substitute this value, 0 equal to a into alpha into 1. So cos 0 is 1, so that becomes 1, minus b alpha into sin 0 is 0, that becomes 0, which indicates 0 equal to a alpha. Here, alpha cannot be 0 because alpha is a function of the p critical. So alpha cannot be 0. If alpha equal to 0, it becomes a trivial solution. So in this case, a should be 0. So which means that v equal to d cos alpha x plus m naught by p critical. The second boundary condition, at x equal to 0, v equal to 0, which means that at the start of the column, the lateral deflection is equal to 0. So we have 0 equal to b into 1 because cos 0 is 1. So therefore, b into 1 plus m naught by p critical, which indicates b equal to minus m naught by p critical. Therefore, the equation v is m naught by p critical into 1 minus cos alpha x. Now, let's go to the third boundary condition. At x equal to L, which is at the end of the column, v equal to 0, which means that the lateral displacement is 0. So we have m naught by p critical into 1 minus cos alpha L is equal to 0. Here, m naught by p critical cannot be 0 because it represents the load, the external load p critical as well as the external moment m naught. Therefore, 1 minus cos alpha L should be equal to 0, which means that cos alpha L equal to 1, which indicates alpha L should be 2 pi because cos is 1 at 2 pi. So we have alpha equal to 2n pi by L. So from the boundary conditions, we have alpha equal to 2n pi by L. So which implies v equal to m naught by p critical into 1 minus cos 2n pi x by L. Now we know that alpha equal to root of p critical by ei, which is equal to 2n pi by L. So when we square on both sides, we get 4n square pi square by L square is equal to p critical by ei. So p critical is equal to 4n square pi square ei by L square. For the smallest root is the first mode of buckling, n equal to 1, which indicates p critical equal to 4 pi square ei by L square. So now let's talk about pinned versus fixed ended Euler columns. For pinned end columns, for fixed end columns, we have the following deflected shape. We have the critical buckling load for pinned end columns, p critical as pi square ei by L square. For the fixed end columns, we have p critical equal to 4 pi square ei by L square. Introducing critical load, we have p critical equal to pi square ei by kl the whole square. Note, k is the effective length factor and then kl is the effective length. So p critical equal to pi square ei by L square. For pinned end columns, the L is 1.0 into L. For fixed columns, p critical equal to pi square ei divided by L by 2 the whole square. So for pinned end columns, the effective length factor k equal to 1.0. For fixed end columns, k equal to 0.5. With this understanding, let's solve the fixed free Euler columns. So when we have one end of the column that is fixed and the other end of the column which is free, we have in the fixed end, we have an end moment m naught acting. At the free end, we have a axial load P that is acting. The length of the column is L and the Young's modulus is E and the moment of inertia is I. The deflected shape is shown here, where when you apply the load, there is a lateral displacement delta at the free end of the column. So we are looking at point A, which is at the distance x from the left-hand side. So when we look at the free body diagram, we have an axial load that is acting. We have a P into delta, that is the moment acting at the fixed end. And then we have a lateral displacement V acting at point A at a distance x from the left-hand side of the column. We have an internal resisting moment, Mi. We know that M equal to minus Ei into d square V by dx square, which is the moment curvature relationship for small deflection. Internal moment, Mi, is equal to minus Ei d square V by dx square. The external moment, Me, is equal to P into V minus P delta. For equilibrium, taking moment about point A, we have Mi minus Me is equal to 0. So we substitute the same from the top equations. We have minus Ei into d square V by dx square minus P into V plus P delta is equal to 0. When we further simplify, we get Ei into d square V by dx square plus P into V equal to P delta. Substituting P critical for P, we have Ei into d square V by dx square plus P critical V is equal to P critical into delta. Now this can be further simplified by dividing by Ei. We have d square V by dx square plus P critical by Ei into V is equal to P critical by Ei into delta. Or we can say that d square V by dx square plus alpha square V is equal to alpha square delta, where alpha square is given as P critical by Ei or alpha equal to root of P critical by Ei. The solution for the ordinary differential equation is V into A sin alpha x plus B cos alpha x plus delta. Now the first two terms, A sin alpha x plus B cos alpha x, represents the complementary solution. The delta represents the particular solution. How did we get delta? Now let a constant C be the particular solution for the ordinary differential equations. A constant is chosen because the non-homogeneous part is a constant, which is delta. So we have d square V by dx square plus P critical by Ei into V is equal to P critical into delta by Ei. Substituting C for V, we have d square into C divided by dx square plus P critical by Ei into C equal to P critical into delta by Ei. Since it's a constant, d square C by dx square becomes 0. So we have d square C by dx square plus P critical divided by Ei into C equal to P critical into delta by Ei. Since C is a constant, the first term d square C by dx square is equal to 0. And then the rest two terms with the P critical is common on both sides and Ei is also common on both sides. So we get cancelled, which implies C equal to delta. So now we get V equal to A sin alpha x plus B cos alpha x plus delta. Now let us find the unknowns A and B from the boundary conditions. The boundary conditions 1, at x equal to 0, we have V equal to 0, which means that 0 equal to A into 0 because sin 0 is 0 plus B into 1 because cos 0 equal to 1 plus delta. So we have B equal to minus delta. Now at x equal to 0, V dash equal to 0 because it's a fixed end, the slope is 0. So we have dV by dx equal to A alpha cos alpha x minus B alpha sin alpha x. The minus term comes because when we differentiate cos, we get minus sin. So we have 0 equal to A alpha into cos 0 is 1. So that you have that 1 minus, we have minus B into alpha into sin 0 is 0. So the entire term becomes 0. Now we have 0 equal to A alpha. Now alpha cannot be 0 for non-trivial solution. So A has to be 0. Why alpha cannot be 0? Because alpha is a function of your P critical. So P critical, if it is 0, then there is no buckling that takes place. So because of which A should be 0. Therefore, V equal to minus delta cos alpha x plus delta is the equation for lateral displacement. We have V equal to delta into 1 minus cos alpha x. Boundary condition 3. At x equal to L, the lateral displacement at the free end V equal to delta. So when we substitute, we get delta equal to delta into 1 minus cos alpha L. The delta and delta gets cancelled, so we have 1 at the right hand side of the equation here. So 1 minus cos alpha L equal to 1. On further simplification, we get cos alpha L is equal to 0, which becomes alpha L equal to n pi by 2. So alpha equal to n pi by 2L. So from boundary conditions, we have alpha equal to n pi by 2L, which implies B equal to delta into 1 minus cos n pi x by 2L. We know alpha equal to root of P critical by EI. So n pi by 2L is equal to root of P critical by EI. So when we square on both terms, we have n square pi square by 4L square is equal to P critical by EI. So P critical is given as n square pi square EI by 4L square. For smallest root n equal to 1, therefore P critical equal to pi square EI by 4L square. Now we have pinned versus fixed free Euler columns. For pinned end columns, we have P critical equal to pi square EI by L square. For fixed columns, we have P critical equal to 4 pi square BA by L square. For fixed and free columns, we have P critical equal to pi square EI by 4L square. So for pinned end columns, K equal to 1. For fixed end columns, K equal to 0.5. For one end fixed and another end free, K equal to 2.0. The K represents the effective length factor. Now let's look at fixed and pinned Euler columns. The left hand side of the column is pinned, the right hand side of the column is fixed. The length is L. E represents the modulus of elasticity. I is the moment of inertia. We have an externally applied moment m0, and to satisfy that, we have m0 by L acting on the left hand side downward direction and m0 by L acting on the right hand side of the boundary at upward direction. So the displaced configuration is given by this one. So the length L is given here. At x from the left hand side is point A. We see that at closer value at point A, we have an axial load P acting. The vertical displacement is given as V at point X. We know that the moment curvature relationship m equal to minus EI into d square V by dx square for small deflection. We have the external moment that is acting, so m0 by L and m0 by L that is acting here. We also have the internal moment resistance mi. So the internal moment mi is equal to minus EI into d square V by dx square. The external moment me is equal to P into V minus m0 into x by L. For equilibrium, taking moment about point A, we have mi minus me is equal to 0, which implies minus EI into d square V by dx square minus PV plus m0 x by L is equal to 0. EI into d square V by dx square plus PV is equal to m0 x by L. Substituting P critical for P, we have EI into d square V by dx square plus P critical V is equal to m0 x by L. Or, which can be further simplified, d square V by dx square plus P critical by EI into V is equal to m0 by EI into x by L. D square V by dx square plus alpha square V is equal to m0 by EI into x by L, where alpha equal to root of P critical by EI. The solution for the ordinary differential equation is V equal to A sin alpha x plus B cos alpha x plus m0 by P critical into x by L. The first two terms is complementary. The third term is a particular solution. How do we get m0 by P critical into x by L? Let C0 into x plus C1 be the particular solution for the ordinary differential equation. A linear function is chosen because the non-homogeneous part is linear, that is m0 by P critical into x by L. The x is the linear portion here. So we have d square V by dx square plus P critical by EI into V is equal to m0 by EI into x by L. When we substitute V equal to C0 into x plus C1, we have d square into C0 x plus C1 divided by dx square plus P critical by EI into C0 into x plus C1 equal to m0 by EI into x by L. We can further expand this one by stating d square into C0 x divided by dx square plus d square into C1 divided by dx square plus P critical into C0 x plus C1 equal to m0 by EI into x by L. The value of C0 is actually 0. The first term in the differential equation is 0 because when you differentiate this one twice, the constant becomes 0. So the term vanishes. The second term also vanishes because the constant is C1 here. It also becomes 0. So we have P critical by EI into C0 x plus C1 equal to M0 by EI into x by L. So when we compare both sides after expanding, we have the following things: C0 into P critical by EI into x plus C1 into P critical by EI is equal to M0 by EI into x by L. So on comparing the coefficients on both sides, we have C0 into P critical by EI is equal to M0 by EI into 1 by L, which implies that we have C0 equal to M0 by P critical into 1 by L because the EI on both sides gets cancelled. And we have C1 into P critical by EI is equal to 0, which indicates C1 equal to 0. So we have the constant C0 equal to M0 by P critical into 1 by L and C1 is equal to 0. Now the solution for the differential equation is B equal to A sin alpha x plus B cos alpha x plus M0 by P critical into x by L. The first two terms represent the complementary solution. The second term is the particular solution. So let us find the unknowns A and B from the boundary conditions. We differentiate this equation to get the slope. So dv by dx equal to v dash equal to A alpha cos alpha x minus B alpha sin alpha x plus M0 by P critical into L. So the boundary conditions are given as at x equal to 0, v equal to 0, which means that the lateral displacement is equal to 0 at the start of the boundary, which indicates 0 equal to A into 0, which is sin 0 is 0, minus B into 1, which indicates cos 0 equal to 1, plus 0 because the x term is there in the particular solution, M0 by P critical into x by L. So when we put x equal to 0, the third term becomes 0. This indicates B equal to 0. Therefore, V equal to A sin alpha x plus M0 by P critical into x by L. At x equal to L, V dash equal to 0. So 0 equal to A alpha cos alpha L plus M0 by P critical into L, which indicates at x equal to L, the slope is 0. So 0 equal to A alpha into cos alpha L plus M0 by P critical into L, which indicates A equal to minus M0 by P critical into 1 by alpha L into cos alpha L. So now we have the values A equal to minus M0 by P critical into 1 by alpha L cos alpha L and B equal to 0, which indicates V equal to M0 by P critical into x by L minus sin alpha x divided by alpha L into cos alpha L. The third boundary condition is given as at x equal to L, V equal to 0. So we have 0 equal to M0 by P critical into L by L minus sin alpha L divided by alpha L into cos alpha L. So 0 equal to M0 by P critical into 1 minus tan alpha L divided by alpha L. So M0 by P critical cannot be 0 because if M0 by P critical is equal to 0, it leads to trivial solution. Therefore, 1 minus tan alpha L divided by alpha L should be equal to 0. So when we further simplify this, we get tan alpha L divided by alpha L equal to 1, which indicates tan alpha L equal to alpha L. We have tan alpha L equal to alpha L. When we plot the two equations, we have x-axis alpha L, in the y-axis we have tan alpha L or alpha L. The blue colored line indicates tan alpha L and the red color line indicates alpha L. The intersection between alpha L and tan alpha L happens at alpha L equal to 4.4934. Now the smallest positive root is alpha L equal to 4.4934. So we know that alpha equal to root of P critical by EI. So 4.4934 divided by L is equal to root of P critical by EI. So 20.1906 by L square is equal to P critical by EI. So P critical equal to 2.046 into pi square EI by L square. When we arrange it, we have P critical equal to pi square EI by 0.7 L the whole square, which is the Euler buckling equation for fixed and pinned condition. Recall, Euler load for simple conditions is pi square EI by L square. For fixed column, critical load is 4 pi square EI by L square. For fixed pinned column, the critical load is in between the two, which is P critical equal to 0.46 pi square EI by L square, or P critical is approximately equal to twice of P Euler. So for fixed free column, critical load equal to P critical equal to pi square EI by 4L square. So here P critical equal to PE by 2, which is 1/2 of the Euler load. The Euler load here indicates the simple boundary conditions. So columns with different boundary conditions, we have pinned end column. The ordinary differential equation is V double dash plus alpha square V is equal to 0, alpha equal to root of P critical by EI. For fixed end columns, V double dash plus alpha square V equal to M naught by EI. For fixed free column, we have V double dash plus alpha square V equal to alpha square into delta. For fixed pinned column, we have V double dash plus alpha square V equal to M naught by EI into X by L. So these are the 4 governing differential equations for 4 different boundary conditions. So the critical load here for pinned end column is pi square EI by L square. For fixed it is 4 pi square EI by L square. For fixed free it is pi square EI by 4 L square. For fixed pin it is 2.046 into pi square EI by L square. We can also represent this in the form of an effective length factor, where K is the effective length factor. P critical is given as pi square EI by KL the whole square. So for the pinned conditions, K equal to 1.0. For the fixed conditions, K equal to 0.5. For the fixed free conditions, K equal to 2.0. For fixed pinned columns, K equal to 0.7. So from this one, we understand that the lowest K factor is 0.5 for fixed, and the highest K factor, which is the effective length factor, is for fixed free columns, which is K equal to 2.0. With this one, we have completed the Euler column derivations for different boundary conditions. In the next class, we'll continue our conversation on stability. Thank you very much.